In this video you will find the dissipation of charge in conductor with time. So first of all we have to consider the fourth Maxwell's equation, that is the Ampere's law. So fourth Maxwell's equation, that is Ampere's law, and this is given by curl of H, that's equal to J plus del D del T. Okay, now we take divergence on both sides of this equation, so we get divergence of curl H equals to divergence of J plus divergence of del D del T. Okay, now by the vector identity we can say that divergence of curl any vector is 0, so that term is 0. That's equal to divergence of J plus divergence of del D del T. Okay, now you can write this J, that is surface charge density, as sigma into E. So that is sigma into E is the electric field, plus, and we can write this term as del del T of divergence of D. Okay, now this sigma is a constant, so it gets out of the divergence of E, plus del del T of divergence of D. Now here we use the Gauss theorem, that is divergence of E is denoted by rho by epsilon naught, and from this divergence of D, that's equal to rho. So you put these values in that case, so you get sigma into value of divergence of E, that is rho by epsilon naught, plus del del T of value of divergence of D, that is rho, that is 0 equal to this. From this sigma rho by epsilon naught plus del rho del T. Now we take these del rho del T terms to the left hand side, so del rho del T, that's equal to sigma rho by epsilon naught, and we can write these terms as minus del rho, that's equal to sigma rho by epsilon naught into del T. Now this can be written as del rho, take this rho to left side, that's equal to sigma by epsilon naught into del T. Now we have to integrate on both sides of this equation, so we get del rho by rho integral, that's equal to sigma by epsilon is constant into integral del T. Okay, now after integrating it we get logarithm of rho, that's equal to sigma by epsilon naught integration of del T is T plus a constant C. Okay, so from this we get that logarithm of rho, taking the negative sign to the right side, we get sigma by epsilon naught into T minus C. So from this rho, that's equal to e to the power minus sigma by epsilon naught T minus C. So that's equal to e to the power minus C into e to the power minus sigma by epsilon naught into T. We take this constant e to the power minus C as rho naught, that is the initial charge density, that is at t equal to 0. So sigma by epsilon into T. Thus we get that rho equal to rho naught e to the power minus sigma by epsilon naught T, and this gives the dissipation of charge density with time, because there is an exponential term, exponential decay term. So charge dissipated with time in conductor.